Dear participants, in this session, we will be considering the behavior of different photosensors or optical sensors. You see, in our earlier sessions, we have come across several sensors like inductive proximity sensor, capacitive proximity sensor, IR switch, through beam sensor, retroreflective sensors, where we have employed the sensors to detect the presence or absence of an object. In further sessions, we have studied LVDT, we have studied RTD, or we have studied thermocouple. Now, a fundamental operational difference that you might have very sincerely followed is the characteristic of the sensor at its output. In case of detection of the object, we have used different sensors like the proximity sensors or the photo eyes. You could have easily followed the output of the sensor is having only two states. Either it is giving a high signal at the output or it is giving a low signal at the output. Normally such sensors have got three wires. One is supplied, one is connected to the supply, other to the ground, and the third pin that gives you the signal. And in order to actuate some further load or relay or a lamp, you have to connect that load in between the signal pin and ground or in between the supply and the signal pin, depending on whether the sensor is of PNP type or NPN type. Now see, those sensors are actually digital in nature. So definitely in our theory coursework, we have come across this terminology, digital domain of sensors and analog domain of sensors. Whenever the parameter that we measure is digital in nature, like the detection of an object, whether the object is present or not, simply this is digital in nature. So therefore the sensor we can use likewise. Now whenever more complex measurements are there, like you can say that we want to measure temperature, that we had done in case of RTD and thermocouple behavior study, or we want to measure precision displacement, that we had done in case of LVDT study, you could have found that the changes in the parameter that we are measuring is continuous. So when you have got changes in the parameter that you are measuring to be continuous in nature, then definitely your sensor should reciprocate with similar behavior. Under such conditions, the sensors are called analog sensors. They are the analog domain of sensor. Now today we are going to study optical transducers or optical sensors. Now you can find that what is our basic target, that I will discuss first. That is our objective of this demonstration session. You can see there is a lamp. As you can find, I am increasing intensity of that lamp simply by supplying a variable signal. We are increasing the voltage across the lamp filament, and accordingly the lamp intensity increases. Now we have to simply study that when the intensity increases or decreases, what is the behavior of these four optical sensors: this pin photodiode, photoconductive cell, phototransistor, and the photovoltaic cell. Now you see, unfortunately this photodiode has been damaged, so I couldn't display its operation, but rest of the things are okay, and we can discuss on them very easily. So first of all, try to look at this arrangement. You can see at the center there is the lamp. Okay, this is the lamp. You can remove it. It's just sitting on a screw type holder. You can find here. Now this is the photovoltaic cell. This is the photovoltaic cell. This square object. You might have seen such things in calculators. Earlier, nowadays those commercial calculators which are bigger in size, they are having this cell. Next you can see here, this is a phototransistor. It is signified by three terminals, the base, collector and emitter. Now you see in phototransistors, the base is actually the terminal with which we are not having that interest, because here you can see, I will just try to show you. You can see there is a lens actually. So whatever light falls on it, it collects. And whenever the intensity of light is increased, current from collector to emitter increases if the transistor is properly biased. That means here intensity of light plays the role of base current. So when the intensity of light increases, base current increases, and definitely your collector current, collector to emitter current is increased. Now see, next, this is the photoconductive cell. You can again find this is simply an LDR. In photoconductive cells, what happens actually that when light falls on them, their resistance decreases drastically. Normally the resistance is very high. You can see here there are two terminals only. There are two terminals. So if you measure resistance between two terminals, then you will find that in absence of light, or when the intensity of light is very small, then you will find the resistance is large. As light intensity increases, the resistance drops drastically. Finally, there is pin photodiode. Remember, whenever light falls on it, this diode conducts, but you have to connect the diode in reverse bias, as we have already studied in your theory course. Now there is a fundamental difference, in this photovoltaic cell and other sensors. The photovoltaic cell actually generates a voltage. Whenever light falls on it, it generates a voltage. I will just show you one thing, that right now you can find there is no supply connected to the board, and even the lamp is not there. So we will try to see whether there is any voltage across the photovoltaic cell. You can find here 0.54, whatever it is, this much voltage is across the photovoltaic cell. Now I will cover it. You can find this is the dark current. This is the dark current. You can see this is because of the dark current, it is in minus. Okay, so you have seen a very beautiful thing, that when it is dark, okay, there is absolutely no voltage, but some finite dark current is there. That's why you can find this negative polarity. Now I will again introduce it to the light, and you can see it is generating its own voltage. We will try to see the pin photodiode. No, it's not generating its own voltage. The photoconductive cell, no. The phototransistor, no. So now you can see this is the basic characteristic of the photovoltaic cell, that whenever light falls on it, proportionally it generates a voltage. All right. Now see, how the sensors are connected, because since already they are connected, we might get confused. You see here, one terminal of the photovoltaic cell, it has got definitely two terminals. One terminal is available here at these test terminals, and other terminal is connected to ground. Likewise, if we talk of the phototransistor, remember these terminals, these test terminals, they are connected to the collector, and the emitter is connected to ground again. In case of the photoconductive cell, the base is not connected anywhere, remember, for the phototransistor. Now in case of photoconductive cell, you will find that these terminals, they are connected to one end of the photoconductor, and the other terminal is connected to ground. I will not discuss about the pin photodiode, so that because we are not going to operate that particular sensor, it is damaged right now. Now you see, you have to remember another point, that these 2 points, these two test terminals, in each case they are shorted. Okay, internally they are shorted, so you can easily find, so that you does not come across any confusion. So you can see that I am in the conduct EA mode, continuity mode. You can find that they are connected and connected. Okay, so I hope you are very clear with the um, constructional feature or the connections of the sensors. Because you see, unless you understand the connections and what is the experimental setup, there is no goodness. I can ask you to just rotate this pot and get the values. Absolutely, there is no uh, goodness out of that, no result out of that. Now you see here, let us look into this board first. You can see this is the input. So this is connected to the lamp filament. Now definitely the lamp filament has to be connected to positive and negative, because it has got two terminals. One terminal has to be connected to positive, the other terminal has to be connected to ground. So here we have to give the positive supply, and the other terminal is directly connected to ground, so we can connect to the ground directly. Actually, this board is very self-contained board. You have got different sort of blocks, as we had studied in the comprehensive trainer of the sensor earlier, that is Scientech 2311. Now you see here there is a comparator block. It compares the signal. Suppose you want to have some sort of application in which you want that output of your, maybe one of the sensors, what is the voltage across that sensor, that has to be compared with some reference signal. So for that you can use this block. Then there is a power amplifier. If the output of the photosensor is very feeble, it's very weak, then you can use this block to increase the power. You can see inside this comparator block there is definitely and comparator IC. In this case it is LM339. This power amplifier, it uses a transistor. This current amplifier, again it uses a transistor, and there is an electronic switch. It again uses a transistor. Different transistors in different configurations have been used. I am not going to discuss in detail of that, because that will create confusion in mind. You see, these are all part of signal conditioning. Now here we are interested just towards measurement or sorry, study of the behavior of the sensors. So we are not going into the detail of the same, only we will use them for our purpose. Now you see that there is a potentiometer. Slide type potentiometer is there. You can see the output of the potentiometer is available across these three pins. These are the two fixed pin, and this is the central wiper. Likewise, there is wire wound pot of 10 kilo ohm resistance. So you can have a variable resistance in between these two terminals A and B, or in between the terminals B and C. You can have this pot, this is a carbon pot of 100k value. You can have a variable resistance in between A and B and B and C. And also its importance is that if you apply some constant voltage at A and ground at C, at this center point, if you rotate this, you get a variable voltage. Definitely that voltage will have less power because of the inherent resistance. So you can use the power amplifier to make it usable for any load operation. Further, we have got a DC amplifier. Again, we have got the input and output terminals ready. We can have a buffer for input and output terminals. Now see that I am not going to use all these blocks. Whatever our experiment require, accordingly we may decide something, right? So what we will do, I will use an external supply to charge this lamp, to put this lamp on and to control its intensity. Because otherwise what will happen, this board will have so many wires and the circuit will become so complex. It will be hard for you to follow. That's why in order to make this thing a little bit of simple, still they will be becoming complex. So I have used this scheme. So you see, I am using an external power supply. Simply that's a variable DC power supply. So I am connecting positive terminal here to the filament, and then I will be connecting the ground terminal. So this is ground. All right. I can simply increase the voltage. I can apply up to 12 volt. That is the limit for this lamp. So you can see the intensity is gradually increasing. Okay. Now I will power this board. Okay. Let us not first power the board. Let us have a look into the behavior of the photovoltaic cell. But before that, what I will do, so that our photo elements are not damaged, we will put this protective cover. So earlier it was there only for purpose of this demonstration of the inside circuitry. I had removed it, so I am getting it back. So that's one screw, and there is another screw. So you see here that although we have covered the sensors, but the cover that we have used is optically transparent. Okay, so in order to make the situation really dark, we will use this cover. So the effect of ambient light, because you see that in this lab right now it is daytime, so sunlight is there, we have got illumination in the lab enough, so that might give us some wrong conception. So when there is no light, what will happen? So for that we will be using this cover very simply. Now another thing is there, that you see that I am increasing the intensity. So when this transparent cover is there, we can very easily follow that yes, fine, we are increasing the intensity and we can expect something at these points, the behavior of the optical sensors. Now when I cover it up, then how can we follow the change? For that, what we will do, we will be using one voltmeter. You can see here, I will show you that I am just trying to measure the voltage across the filament. So you can see this is one test terminal of the filament. This is the ground. So when the intensity increases, you can find the filament voltage also increases simply. So therefore I will be using this meter. So whenever this is completely covered and we can find a voltage here, we know that light intensity is increasing. All right. So now let us first study the characteristic of photovoltaic cell. All right. So for that, I'll be using another meter. So you can find this is another meter, and the photovoltaic cell generates a voltage when light falls on it. So what we will try to do, we will simply try to measure the voltage that is developed across the photovoltaic cell. As we had already discussed that one terminal of the photovoltaic cell is available here. So I will put this terminal here and I will put other terminal of this multimeter to ground, because another terminal of the photovoltaic cell is connected to ground, as we had discussed just few minutes before. Now you see that I will simply increase the filament voltage. Oh, sorry. Okay. So there is no voltage across the very little voltage across that photovoltaic cell. Now I am increasing the filament voltage, and you can find just proportionally the voltage is developed across the photovoltaic cell. You can find. I will go up to 10 volts. So you can see very easily that we are getting voltage across the photovoltaic cell. So this is the basic characteristic of a photovoltaic cell. Now let us study the behavior of a photoconductive cell. Now you see that whenever we are performing this experiment, how we have to perform? We have to note down the voltage that is applied across the filament, and we have to note down the voltage developed by the photocell. So you see that we have got a set of readings. Maybe we can have 15 to 20 readings for different values of photovoltaic filament voltage, and then we have to plot the characteristic. So in x-axis we have to plot the filament voltage, and in y-axis we have to plot the voltage developed by the photovoltaic cell. So in that way we have to perform actually. Here we will not do that. Okay, it will take a lot of time. Next, we will be studying the behavior of photoconductive cell. Now you see, as we had discussed, whenever light falls on the photoconductor, its resistance changes. So here we are interested in measuring the resistance. So what we will do, we will take this multimeter to the resistance measurement mode, ohm meter mode, and again the photoconductive cell has got two terminals. One terminal is available in these test points and the other terminal is connected directly to ground. So I will be the photoconductive cell here. Now you can see the resistance range that I am using in this multimeter right now, it is 2 mega ohm, and you can see even that is unable to measure the resistance. So that means the resistance of the photoconductive cell in absence of any light is more than 2 mega ohm. It is very clear. So now I will be increasing the voltage. You can find here I am increasing the voltage, right? So I am gradually increasing the voltage. You can see immediately the resistance is decreasing. You can find here. So I will get lower value. So you see right now we have very little light here, you can see the situation of the lamp. Still you can find the resistance is very low. As I will keep on increasing the filament voltage, you can find the resistance now, the resistance value is very less. Okay, you see? Yeah. So in 2K range, it's 0.737, that means 737 ohm is the resistance. So as you can see, but definitely the resistance will not be completely zero at any point of time. Okay, now I will give the ambient light also. You can see the intensity is completely full. So you see these things are very sensitive. The optical sensors are normally having very high sensitivity. Now I will be interested in studying the behavior of this phototransistor. Now while we want to study the behavior of phototransistor, we have to go for some additional circuitry. Let us try to understand that. What we will do. You see, this is the phototransistor. This is an NPN type transistor actually. The emitter is connected to ground. This indicates that we are talking of a phototransistor. And you see, this is the test terminal. So the collector is directly connected to the test terminal. There is no additional, I should say, component. Now what I will do, I will simply put on light at the base of the phototransistor, and my objective is to see that how much current is flowing through it. So what I can do very simply is I will use the onboard 5-volt supply. Alright, then I will be connecting a resistance. Now you might be confused at this point because this board has got no fixed resistance. What I will do, I will use one of the variable resistance and employ the center terminal and one of the end terminals so that we can get a resistance. And then I will be connecting an ammeter. So this will be positive terminal of the ammeter, so negative terminal we will be using a milliammeter. So we will actually using this particular scheme to measure what I will say the photocurrent. Because of this photo falling on the base, we are getting a current. So we will be measuring that current. So let us try to build this circuit. Now you have to follow very closely, otherwise you might get confused. So you see here, I'll be using this pot. So I will be initially removing this. So this is the terminals for that I will, this is for lamp filament. Okay, there is nothing connected in the board right now. Now we will be starting our connection. What I will do, I will simply use this 5-volt point that is on board facility given by the manufacturer. I will connect it to one end of the resistance. Alright. Now I will connect, and let us also find what is the value of resistance. We can also do that. There is absolutely no problem. So you might be interested in knowing how much value of resistance we are giving. So I think there is some problem with this resistance, so I'll be using that maybe. Yeah, okay, it might so happen that this meter has got some problem with its resistance range, so we're using another meter because both the potentiometers cannot be bad in shape. This is working fine. So you can see that I will set maybe 50k. Okay, let us skip, or 10k, let us skip 10k. 50k will be too high. So this resistance is also required, so that uh, any damaging current, so if the current is very high, that might damage the transistor. So I'll be keeping the value of 10k. Okay, so in between these two terminals the resistance is right now 10k. Now we will not disturb this. Okay, so I will be connecting the 5 volt pin here to this point, so that this point is right now at 5 volt when we connect the supply. And now I will be using this meter in as an ammeter. So here we have got positive terminal of the ammeter because current is flowing in this direction, and here I will be connecting the negative terminal of the ammeter to the phototransistor collector, as we had seen in this circuit diagram. Okay, you can see here we have to start from the 5 volt. There is a resistance of 10k, positive terminal of the ammeter, milliammeter, and then negative terminal of the milliammeter, which is connected to the collector. So this is the same thing that I am using. Alright, so now we will be going for the onboard supply. So we will confirm whether we have got the 5 volt properly working or not. You can see I am right now in the voltage range, and there is a problem to accommodate both of them, but still okay. Yep, you can see here. Oh, I'm sorry. Yeah, that's about 5 volt. Okay, now let us try to measure the lamp filament voltage, and we will see. You can find you are having some collector current. So we can see that there is not enough collector current. So what I will do, maybe I will decrease the collector resistance value. So now you will see that you will have a significant collector current. I hope this is clear. I can further decrease this resistance so that you can have more collector current. Alright? Or you may do one thing. You may go for maybe lesser resistance to see a heavy inflow of collector current. You find here. Alright. So you can see I will be making this resistance very low. Now you can find that yes, there is increase in collector current or the photocurrent to the phototransistor. Now let me tell you one thing, that whenever you are using this sensor for some photo switching applications, then remember that you have to always use a resistance like this. All right, remember that we have to use a variable resistance. Why? Because at what value of current you want the switching to be done. Now this is a very arbitrary statement, what value of current. Actually, we are interested in knowing the voltage across the phototransistor. Because you see here, if you look at this circuit and you are very interested to apply KVL over here, you can find when there is no light, falling on the base of this phototransistor, you will be having the entire voltage across collector and emitter in between these 2 points. Why? Because the transistor is not conducting. So all voltage will be available across this collector and ground, because the emitter is directly connected to ground. Now, if light falls and the transistor started conducting, you will have fall across the VCE. That is, you will have a fall in the value of voltage across collector to emitter, that is VCE. Now, why it will happen like that? Because now the transistor has started conducting current, and therefore there is a collector current. Since there is a collector current, there will be a voltage drop across this collector resistance. Now, when there will be voltage drop, you can very easily find that KVL shows that there will be a decrease in the value of VCE. This is very important to understand. Therefore, in order to have a control over this voltage drop, always use a variable resistance here. Whenever you are doing a project of photo switches like that, you will come across the problem with a fixed value of resistance. So it is always better to use a variable resistance over there. Now we have completed the basic or the fundamental objective of studying this behavior of the photo elements that we wanted to see here. Now we will look into the applications, because as per your syllabus you can see that there are 2 experiments on these photosensors, and there is experiment on photo switching application also. So in this demonstration session we will be covering all aspect. So we are moving towards the second part of the experiment. First of all, let us see that what is one element of the board about which we have not discussed yet. You can see there is a relay here. Now I will just go with the basic operation of a relay as a revision. You know that there is a coil inside a relay. One terminal of which is connected to ground. We are talking about relay operation, and other terminal we have to connect it to supply. It depends. If it is a 6-volt coil, you have to apply 6 volt. If it's a 5-volt coil, you have to apply 5 volt. It can be a 12-volt coil or a 24-volt coil likewise. Now see that these are the 2 terminals, terminal 1 and terminal 2, that you find in any relay. Further, there are 3 more terminals. One is a common terminal, one is the NO terminal, and other is the NC terminal. Now the operation of relay is very simple. You can see that whenever we pass signal through this coil, there is an electromagnet. All right. There is an electromagnet. Now what is that? Whether this electromagnet is a separate entity? No. It is the coil itself. So we can say that we will pass current through this coil. This is our terminal 1 and this is our terminal 2. Now we can forget this. So when we do this, this becomes a magnet and it will attract a switching element towards it. There is a spring loaded mechanism. Maybe if I make the drawing like this, it will be easier for you to understand. This is the coil. Here you have to apply the signal, and here you can think something like this. This is just a uh, there is no electrical connection in between this. That's why I have shown this dot, and here there is a spring. All right. So you can think in this way, or the spring should not be here. If you can think of the construction, spring should be here. Okay. Now you see that whenever the coil is energized, this is the switching element. The switching element will be drawn towards the coil because this has become a magnet. So if earlier this was the switching element condition, whenever this relay is energized, this element will have this as the position. So the position will change. And when we remove the signal, because of the action of this spring, this switching element will be back to its home position. So I hope that this is very clear, that this is a switching element. Whenever the coil is energized, it will move like this. It is under the tension of the spring. Whenever we remove the signal, because of the spring, it will get back to its own condition. Now, the constructional feature is like that. Here you have one terminal. This terminal is called common. Here you have another terminal, which we call as NC. And here you have another terminal, which we call as NO. All right. So what is the significance of this NC and NO? You see, this NC signifies normally connected or normally closed, and this NO is normally open. So now you can find that normally closed means it is closed with the common terminal. This is the common. And when the relay is energized, this, because of the action of the switching element, this common terminal gets connected to NO. So now this terminal is connected to the common terminal under the action of this coil. So you see, if I connect a 5 volt here at the common terminal, so when the coil is not energized, you will be having that 5 volt at this NC terminal. And when I apply a signal here in the coil, because of the actuation of the switching element, you get the 5 volt across this NO. So this is the basic operation of a relay. Let us see here. Here we have got a relay. And see, this is an input terminal. The input terminal signifies one end of the coil. The other end is directly connected to ground. There is NC, there is common, there is NO, and you can find an LED input. All right. So the LED input is connected directly to the anode of the LED, and cathode is connected to ground through a resistance, so that you do not allow a damaging current to pass through the LED. Now let us try to operate this relay first. So how we can know that there is an operation of the relay? What we will do, I will simply apply a 5 volt to the common terminal. So when I apply the 5 volt to the common terminal, we will see that this is the LED input, and we can find this NC is connected to the 5 volt. Since you can see the LED is now glowing. All right. So with NO, it's not working. Fine. So what we will do? We will now connecting the LED to the NO, and now we will try to energize the relay or the coil. So for that I will be using this 12 volt, which is an onboard facility. I will give to the input. Now you can find, if I connect it to the NC and I de-energize the coil, you can find the LED is working. Why? Because common terminal is connected to the NC. I will put the input, it is off. Now I am connecting the LED to the NO, that is normally open. When I apply the input, you can find the LED works. Now this common terminal, which is having 5 volt, it is connected to the NO. So this is the basic operation of the relay. Whenever you are trying to go for a photosensor based switching operation, relay is inevitable, because you only do not want to just work on an LED, because LEDs might work with the help of the voltage that is developed by a photocell or something, but you want to actually energize AC load or heavy load with that. So for that, relay will give you necessary support. Now first of all, we will try to see how this comparator becomes such an important entity here. So for that, what I will do, I will put a reference voltage, or I apply a reference voltage in terminal B, and further the voltage across this photovoltaic cell will be applied in terminal A. You will find that how the output changes in correspondence to the relative value in between these two terminals A and B. So we will do a very basic um, circuit arrangement. For that, you can see this pin, this red pin, this is connected to jumper, this is connected to this 5 volt. So I will get this 5 volt uh, to one terminal of the sliding potentiometer, and we will connect another terminal, fixed terminal of the potentiometer, to the ground. So now you see we will be having 5 volt across the potentiometer, 5 volt across the potentiometer. Now the fixed terminals, now I will be using this variable terminal. Let us check whether we get a variable voltage here. You see, this is simply a voltage, it does not have the power to drive any load. That you have to be very careful about. Many times it happens that we try to drive a load, if the load is having very little power necessity, then it may be driven. So don't try to drive a load while using a potentiometer. You can see I'm having variation here. So we can find, I will try to get some intermediate value, maybe 1 volt. Okay, so that I will be using as a reference voltage, but whether that reference voltage um, will be sufficient for us, that we have to see. So we will again go back to the photovoltaic cell. This is the output of the photovoltaic cell, and I am applying some light. Uh, oh, sorry. That's why there was some problem. I was sorry, extremely sorry. It was now you can see. Yep, you can find you have gradual change in voltage. Earlier it is in ammeter range. I'm sorry, you can see this. Okay, so we can uh, have any value that we want for the reference voltage. Now we will be trying to measure the photo voltage, so that we can see its range. So you can find that okay, we are having something around 0.94 volt. So for the reference, we have to go below this. So we will be going for zero point 0.8 volt reference signal. So let us go for that. Okay, I'll be going for 0 0.8 volt. All right, or maybe 0.7. Okay, so you see 0.7 volt is the voltage that is available in this pin. You can see here, I don't want any confusion. You can see it's 0.7 volt. Okay, so I'll apply it here. So this is the reference terminal of the comparator. I'll make it 0.7 volt. All right, just by using the sliding potentiometer I have done that. Now we will see the span of the operation of this photovoltaic cell once again. Okay, you can find it can go well below that, above that 0.7. Now you can see I will be applying the output of the photovoltaic cell to the test terminal of the comparator. Okay, so now you see here the condition. What is the voltage at this yellow pin? You can see it is the reference terminal. We have got, I will make it lesser, 0.5 I will make. So you can 5, it is around 0.5 volt. All right. Now what is the voltage across the photovoltaic cell? 0. So now the interesting thing will happen. Let us see what is the output of this comparator. You can see it is 11 volt. Okay. What does that mean? That means that the reference signal has to be fed to pin number 1, or vice versa. There is no difference actually. Okay. Now you can find the reference signal is given at pin A, which is 0.5 volt, and voltage across the photovoltaic cell is 0. So the output of this comparator is 0. So now what I will do, I will see when the comparator switches. Okay. So for that we have to use two meters actually. I will be introducing another meter. We no more require the filament potential. So here I will be seeing the voltage across the photo cell. Now you see this meter that gives you the voltage that is developed across the photo cell, and that is the output of the comparator. You kindly look at both of them. We know what is our expectation, that whenever the voltage across the photo cell is beyond 0.5 volt, then the output of the comparator should give you a signal. Okay, sorry. Here I have to give. All right. Now I will increase the photo voltage. You can see in this meter, the meter that I am right now oscillating. So it should go beyond 0.5 volt to get an output from the comparator. Okay, it's very small. So I will be, maybe I will change the reference potential, because the photovoltaic is not able to generate that much voltage. So what I'll do, this reference signal I will decrease. I will decrease the reference signal to 0.15. Okay. Now the reference signal is 0.15. The output of the comparator is 0 because the photo voltage is 0. So right now our expectation is that when the photo voltage is beyond 0.5 volt, 0.15 volt, then there will be change in the state of the comparator output. You see here where my finger is, you look at this reading: 0.6, 0.7, 0.8, 0.9, 0.1, 0.11, 0.12. Still you can find it is 0.13. The output of the comparator is low. Now you can find the output of the comparator has switched from almost 0 volt to 12 volt. Now what is the voltage across the photovoltaic cell? 0.19 volt. Again you see, if I decrease the intensity, light intensity, you can find this is a switching from no output to full output. So that you can use the output of the comparator can be fed to a relay for its operation. Okay, that we can do actually. Actually what happens that this relay needs more power, so therefore you have to use the power amplifier or this. Or we can give it to an electronic switch, because this power amplifier has got some problem. We're giving to this electronic switch. Yes, there is an operation of the relay. So now we will see that how it happens. Okay, we will simply check the voltage across this photosensor and we will look towards this relay. So I will connect 5 volt to the common, and I will be connecting this NO to the LED output. Alright, now you can find, we know that beyond 1.5 there will be switching. Observe closely. Now you can see beyond 1.5 the LED is on, because the output of the comparator is now fed to an electronic switch. It is giving the output and that output is driving the relay. So you can find this output is connected to the relay. So again you can see, if I decrease the photo voltage, so that's it. Now in the third part of this experiment, we will try to develop a circuit that will operate in such a manner that whenever there is darkness, then it will operate the LED to on, and when there is light the LED will be off. So this application is also called a Twilight switch, and you can definitely develop this basic project as an assignment for yourself. In order to develop a Twilight switch application, let us consider a circuit like this. Let us have this point as supply. We will need a resistance, and then we will connect the phototransistor. Here we will be giving 12 volt, and collector voltage will be fed to the electronic switching block. Output of this block will be given to the relay. Let us now try to understand the operation of this circuit. When there is no light, that is dark condition, this transistor will not conduct. This transistor will not conduct. So what will happen? Voltage will be available across the transistor, so that this electronic switch will be activated and you will be having a high signal here. So when there is dark, you will be having a high signal and your relay will be operated. Now you can simply use the NO terminal for your operation if you have connected a supply to the common terminal. Now when light will fall on the transistor, collector current will start flowing. So there will be a voltage drop right now across this collector resistance. There will be voltage drop here. So voltage across the transistor will drastically decrease. So your electronic switch will become deactivated and your relay will also become deactivated. So let us now build this very simple circuit here. We have got all facilities on board, so there is nothing to be worried actually. We will use this pot for the collector resistance. So we will be using only these A and B terminals. Okay. So we connect the 12 volt here. This is 12 volt. Maybe I will come here. This is the 12 volt, or I will remove everything from the circuit so that we are not confused. So you can see 12 volt is connected here. Next we will carry this 12 volt. So this 12 volt, then the resistance, then we have connected to the collector of the phototransistor. You can see here 12 volt, then the resistance is there. This is the resistance and there is collector of the phototransistor. That's it. Now output of the phototransistor will be fed to the electronic switch. So let us do that again. Electronic switch. Okay. Now output of the electronic switch will be given to the relay coil terminal, as we had already discussed in the earlier part of this experimental session, that one terminal of the relay is already connected to ground relay coil and other terminal is available here. Now in order to operate the diode in common terminal, I will be connecting 5 volt, and now this NO terminal, which is normally open, it is connected to the LED input. All right. Okay. Now see that our circuit is ready. What we will do? We will now give our onboard supply so that the transistor is biased. Okay. Now I will not cover it purposefully. I will show you the reason. Now I will go for the lamp filament. All right. So you can see right now there is no light. Okay. The ambient light, I can also manage it. We can also manage it rather, but we will see later on. There is no light because the lamp should be on. Now you can see I am putting the lamp on and I will gradually increase the intensity. You can see the LED is off. Note here. So you can think of this that way, that the sun is rising, sunlight is strong, and now your light is off. Here you may want that even this light, because right now there is ambient light, even under such a condition your LED should be off. How you can do that? Now you have to control this pot. You have to control its value in such a manner. Here it is not possible. Maybe you need a larger pot, larger value, but you can do it. Okay, you need separate value of resistance. No problem. We'll see it here. I will cover it up. Okay. All right. Now you can see. I will remove this. You can find. What is the usefulness of this variable resistance? Let us try to find. Here you can see that it is off at quite a significant intensity of light. You want that at a lesser intensity it should be off. Then you have to work on it. Now you can see this is on, right? I will take the intensity much lighter. Okay, this is on. You want it to be off. You can see. So you can change this value of collector resistance to decide at what intensity of the ambient light this LED will be energized. Now you can see that even if there is very feeble light, the LED will be off. Now I will again get the back. I will make it minimum. Now you will see that you need a very, even at that intensity, the LED is working. Why? I have kept the value to be minimum, this resistance. Now you see. Okay, I will increase this. At a later lesser intensity right now, the LED will be off. I will increase the value. You can see such a small change of intensity can be read. So this is the switching application. So you can very simply make this happen if you use, if you make this switch ready, then what will happen? You can simply make a project by which you can control maybe the porch light of your house so that it gets automatically on and off with respect to sunlight. Okay, so this is all about this long session. I am sure you have enjoyed, and definitely for any of your confusions you can come back with your comments so that we can get back to you with the answers. Thank you so much.